Hi, I'm Chen from Zhejiang University. Today I'm going to talk about our recent work on the security autonomous vehicles, which is rolling covers, adversarial laser exploits against traffic light recognition. This work is collaborated with Zhijian Xu, Zhanyuan, Dr. Xiaoyu, and Dr. Wenyuan Xu. Let me get started by introducing traffic light recognition. Traffic light recognition is a system that enables vehicles to detect and recognize traffic light signals. It is essential for full autonomous driving, especially in urban areas, and companies like Tesla have already implemented this system on their vehicles. So how does traffic light recognition work? There are 3 steps. First, a camera captures the front view of the vehicle into an image, and then the image is processed by the traffic light detection model, which detects the presence and position of the traffic lights in the image. And finally, the traffic light recognition model recognizes the color of the traffic light. Well, what will happen if the traffic light recognition goes wrong, such as generating a wrong output? The consequence is pretty obvious. If a red light is recognized as a green light, the vehicle may run a red light and cause intersection accident. If a green light is recognized as a red light, it may cause a sudden stop of the vehicle and potentially lead to rear-end crashes. So from a security perspective, we wonder, is it possible for an attacker to make the above accidents happen by spoofing traffic light recognition? Well, it is possible. At least you could use fake traffic lights, and a few cases have demonstrated the feasibility. However, it is probably not the best idea because fake traffic lights are easy to detect and difficult to deploy in practice. And in this study, we use laser. A laser is a form of light that has a very narrow beam of radiation, which means that it can travel a long distance and is hard to detect. Some previous studies have shown that laser can interfere with cameras, such as blinding the camera and makes it impossible to recognize anything in that image. However, in our attack, we need something different other than blinding. Here's the attack scenario. The attacker generates a laser signal using a laser diode, and she shoots the laser into the target camera. The interfered image will go through traffic light detection and recognition, and hopefully it may cause a wrong output of the system. To achieve a successful attack, we envision that there are 3 requirements. First, the laser interference has to affect the image as little as possible so that the attack can be more stealthy. Second, the attacker has to ensure that the traffic light can still be detected under the laser interference. And third, the traffic light has to be recognized as being in a targeted color. And these 3 requirements have to be achieved at the same time, and it is unknown whether this is possible. For the first requirement, we studied all the possible effects of laser interference. The most common effects are overexposure, color shift, and white imbalance. However, none of this is what we want because the laser affects the entire image and can be easily detected. So to make the attack stealthier, we designed a new method that can inject a color stripe into the image that only overlaps with the traffic light region. So how to generate a color stripe? We exploit the vulnerability of the rolling shutter mechanism. In all cameras, there is an image sensor that is made of an array of color sensing pixels. A rolling shutter means that the pixels are recorded line by line instead of capturing the entire frame all at once. In this way, the first line is recorded first, and then the second, the third, and so on in rolling sequence. The problem of this design is that when you're taking a picture of something that is moving or changing fast, then you will get some odd pictures like this. And it is all because the different parts of the image are not captured at the same time. And unfortunately, most cameras use rolling shutters, including those on vehicles. By exploiting the vulnerability, we can inject a color stripe into the image using a laser pulse signal. The color stripe will only appear on the lines that are recorded at the same time when there is a laser interference. By adjusting the laser pulse parameters, the attacker can have full control over the stripe's number, width, and position. And by synchronizing the laser pulse with rolling shutter period, the attacker can make the stripe appear at the same position in continuous video frames. As for the second requirement, the injected color stripe must not affect the traffic light detection. We find that there are two requisites. The first is a proper control of the laser intensity, because if the laser is too powerful, it can hide the traffic light. The second is a proper design of the stripe's width and position. For example, the color stripe can cover the entire traffic light or only a part of it. Our experiments show that for both red laser and green laser, the accuracy of traffic light detection is barely affected if the stripe covers the entire traffic light region. For the third requirement, we consider both red to green and green to red attacks. Our preliminary experiments show that the attack is feasible, but it is also non-trivial. For example, in the two figures, we sweep the laser's intensity and measure the confidence score of the traffic light recognition. We find that to achieve a successful attack, the laser's power needs to be in specific ranges or values. And besides the laser's power, we find that the attack result is also affected by the laser's incidence angle, the traffic light itself, and even the image background. And therefore, to ensure a high success rate, the attacker needs to fine-tune the laser parameters according to the specific traffic lights and attack scenarios. Based on the above observations, here is our threat model. Before the attack, the attacker prepares a set of pre-recorded images of the target traffic light. Then she simulates the attack in software and finds the best combination of effective laser parameters that can spoof traffic light recognition. During the attack, the attacker generates a laser using the effective parameters and shoot the laser into the target camera. And hopefully, the laser can produce the attack result similar to the simulation. To generate the laser signals, there are several key attack building blocks. The first is the attack modeling that simulates the laser interference, which involves camera modeling, laser interference modeling, and laser effect emulation. Then we use gray search to find the effective laser parameters. And finally, we map the laser parameters to real laser signals. And due to time limits, please refer to our paper for more details. We have evaluated the attack in the real world on 5 cameras and 2 state-of-the-art traffic light recognition models. And one of the cameras is the actual sensor used on Tesla vehicles. In the stationary setup, the laser, the camera, and the traffic lights are fixed in various distances, positions, and directions. We measure the attack's overall performance and study the impact of the traffic light. For the overall performance, the average success rate is 20% for the red to green attacks and 45% for the green to red attacks. It is actually good news because it suggests that running a red light will have a lower chance than a sudden stop. The attack performance also varies depending on the camera. And to our surprise, the camera used on Tesla is the most vulnerable to our attack. The performance is also affected by the traffic light's distance, position, and direction. For example, the attack success is lower as the traffic light is more far away, within 25 meters. And success rate is higher when the traffic light is in the middle of the image. We have also evaluated the attack on moving vehicle from 3 perspectives: the effectiveness across continuous video frames, the feasibility of tracking and laser aiming, and the end-to-end impact on driving. We find that for both red to green and green to red attacks, the attack can continuously spoof traffic light recognition for more than 1 second with a success rate of 85%. And to facilitate camera tracking and laser aiming, we built an attack equipment by combining the laser dial and the telescope. Using this equipment, the attacker can inject laser into a vehicle's camera from 40 meters away, even if the vehicle is moving at 20 kilometers per hour. And due to the unstableness of manual aiming from a distance, the success rate is slightly lower than the stationary setup. We studied the attack's potential end-to-end impact polo running in the LG SVL driving simulator. The simulation shows that the attack is sufficient to make the vehicle run a red light or make an emergency stop. To mitigate the threat, future cameras may use global shutters more instead of rolling shutters. And we also propose to improve rolling shutters by switching to a random rolling sequence that can dissolve the color stripe. In summary, in this work, we propose an attack that exploits the vulnerable rolling shutters in cameras. The attack can spoof traffic recognition using laser and potentially cause self-driving accidents. And I guess the key takeaway message here is that when designing future systems, we need to consider the limitations of the hardware, and we should never ever trust the sensors for granted. And that's all of my talks. Thanks for listening.